Again, a brief presentation overview will be cover, basically a little bit about the project, discuss briefly the UHPC selection and design elements, and then Michael will finish up with some discussion relative to construction methods employed, and will provide conclusions at the end of the presentation. This project is a PennDOT sponsored project located in the city of Philadelphia, about 2 blocks west of the 30th Street station. It's on JFK Boulevard over SEPTA's Walnut Street Tunnel. The bridge owner is the Pennsylvania Department of Transportation. The bridge was constructed in 1955 by the state. The structure is mainly a 2-span structure comprised of non-composite concrete encased rolled steel I-beams, or a combination of built-up girders in a few locations with exposed bottom flanges. All spans have a concrete deck that is continuous over the interior supports. The span lengths vary by location, and the beams are mainly oriented basically perpendicular to the direction of traffic, obviously, which is 90 degrees from normal. And then the substructure consists of a reinforced concrete abutment caps on top of a stone masonry wall on the west side, and a basically reinforced concrete cantilever abutment on shallow concrete foundations at the east, and a steel pier bend, which we're basically going to be talking about today, comprised of rolled steel I sections, HP sections, columns with an upper steel diaphragm and a lower concrete steel concrete composite railroad crash strut, which is all supported on a shallow concrete foundation also. And again, the picture you see there basically is giving an overview of the whole entire site there. Oops, there we go. Our Benish & Company was designer of record for the project. This was the first rehabilitation project on this bridge since it was opened to traffic in 1955. The main scope of work included bridge joint replacement, concrete deck repairs, and critical steel repairs and member replacements. The scope was focused on repairing the structure to the degree required to remove the current 15-ton load posting on this bridge. The project was bid in early spring 2020 and was awarded to AP Construction for a total construction cost of about $15.6 million. The single element driving the use of ABC techniques was the SEPTA's regional rail airport line, which operates through the Walnut Street Tunnel to 30th Street Station, which runs 7 days a week, basically from 5 a.m. to 12 midnight, with trains scheduled at least every half hour. I think there's like 185 trains a day that go through this tunnel. Through coordination with SEPTA, it was agreed to schedule basically a 3-week rail outage with substitute busing provided by SEPTA from the airport to JFK Boulevard for drop off and pick up right adjacent to the 30th Street Station as the most efficient and least disruptive to SEPTA's passengers. Construction began in March of 2020, which also coincided with the statewide COVID shutdown. The project was able to proceed under emergency authorization by the governor, and the actual airport line was permitted to be, the actual closure of the line, outage of the line, was permitted to be extended to 7 weeks due to low ridership during the COVID pandemic. The short construction duration made UHPC the preferred option for strengthening and protecting the steel columns. The project called for UHPC to also be used on the deck closure pours and the pier bend column repairs. The project specified PennDOT standard special provision mix for UHPC with additional minimum compression strength criteria of 12 KSI in 12 hours using accelerated heat curing before significant loading of the deck and columns were allowed. The UHPC concrete provided additional compressive and buckling resistance to the steel columns to compensate for the steel column section loss that was not to be played, not to be repaired, and also protected against future corrosion of the column bases and the moist tunnel environment. Due to COVID, during the COVID thing, the 12-hour curing requirement was waived during construction, and deck pours that were originally scheduled for UHPC end up using conventional concrete because of the COVID shutdown. As you can see on the slide, the left photo shows the existing column bases with the concrete encasement removed. Note that there's significant section loss to the flanges. A middle photo shows the extent of the column section loss along with temporary repairs. And again, some of these locations required the whole column to be replaced. And the right photo also showed some of the twin galvanized column replacements that were done at each deck joint. Again, the last slide I have basically on the slide, the left side shows the existing concrete pedestal removal, and the right side shows proposed column pedestal repair with UHPC. The existing column basically was short, had short pedestals right at the existing ground line, which subject them to frequent saturation during storm events, which caused the advanced corrosion of the columns, their bases through the water wicking process. The proposed design detail removes the concrete encasement, leaves up to moderate steel section loss in place without repair, and followed by blasting and priming the remaining column. Then UHPC concrete encasement was placed around the column bases up to the underside of that collision strut, which will provide for future protection for the lower portion of the columns. And basically at this time, I'd like to hand the presentation back over to Mike this time.
Thank you, Joe. All right, hopefully you guys can see my screen now. So I'm going to talk about the construction of the UHPC. You can see in this photo the formwork. This is for the lower portion of the pedestals, the part that would encase the steel base plate assemblies. And make sure I can advance. There we go. And then there's a second upper portion of the formwork that was constructed. In these photos, the formwork that are visible are complete. Just to give a sense of scale, the center photo has obviously a person in it. That's actually Bo Kolish, the president and inventor of Steel Like UHPC. In the right photo, if you look closely, you can see some spray foam. There's a lot of head pressure here, so they need to make sure those forms were sealed tight. So once again, Steel Like mixed the UHPC in locally available ready mix trucks. And again, Steel Like, for now at least, is the only commercial UHPC supplier able to do that routinely and successfully. Here you can see them loading the material into the hopper of the ready mix truck. Then the next step was adding water to the truck to liquefy the UHPC. And then once the consistency was ready, steel fibers were added to the truck to complete the mixing process. So using a ready mix truck brought a number of advantages to this project. First of all, large batch sizes, 6 cubic yards per batch. We could have done up to 7. And the unique properties of Steel Like UHPC facilitate low energy mixing, which like what happens in a ready mix truck. And so this reduces the heat buildup during the mixing process and allows the mix to stay alive for 1.5 hours or more. So once UHPC was mixed, now it needs to be delivered to the forms down in the tunnel. So in consultation with Steel Like, the contractor decided to use a Trammy and mix the UHPC above and outside the tunnel. And here they are lowering the Trammy through the openings in the deck and then dropping it down into the tunnel below. And now it's in position ready for UHPC. So the Trammy was a 6-inch diameter for the majority of it, but it had a 4-inch reducer at the bottom end. The repairs were 30 feet below the deck surface, and due to limited openings from above, the Trammy line had to be up to 70 feet long in order to access all of the column repair forms. In this photo, you can kind of see the Trammy line here coming down from above and into a form down here where the workers are. So once the Trammy was in place, the ready mix truck, which was parked nearby but away from other activities for the mixing process, simply drove up to the Trammy and discharged directly into the Trammy line. So this represented more advantages to the project. Again, UHPC was mixed not inside the tunnel, but outside the tunnel and above on the top surface, away from the construction area, and was able to drive up to and discharge directly into the Trammy. This avoided creating congestion in the construction area and also saved time and reduced waste versus transferring material in buggies. Additionally, each column repair required about 1.5 cubic yards of UHPC. So by having the large batch sizes of a ready-mix truck, the contractor was able to fill up to 4 column repair forms per batch of UHPC. In total, there were 50 column repairs, so a total volume of 75 cubic yards. And those were filled with 13, but probably up to 20 batches, because not every batch used the 6 cubic yard volume. But contrast that with 58 cubic yards or 58 batches or 116 batches if the contractor were to use the traditional mixing equipment for UHPC. 58 if they use the horizontal shaft high shear mixers, or 116 if they use the vertical shaft high shear mixers. So that, again, the ready-mix truck saved a lot of time, reduced the number of batches. Additionally, there was one occasion where, well, probably multiple occasions, but where the contractor stopped the UHPC discharging in the middle of a batch due to form leaks down in the tunnel. In one particular case, the contractor had a hard time sealing up that form, and the steel like was kept in the UHPC truck for more than 2.5 hours in 80-degree temperatures and higher. And steel like was able to keep the material workable and fresh and alive for that whole time, and never had to waste any material. So once the material was in the form, it started to gain strength. As Joe mentioned, there was initially a requirement that it reach 12 KSI in 12 hours, which steel like could achieve with heat, but that requirement was relaxed, so heat was not used. And we then reached the required 28-day strength of 21.7 KSI at 28 days, with one set of test cylinders lagging behind a little bit, but that caught up more than enough by 56 days, at which point the average strength of all the test cylinders was 24.8 KSI.
You have 2 minutes left, Michael.
Okay, perfect. So these are just some photos of the completed repairs. The photo on the left still has the forms on the bottom portion surrounding the steel base assembly. Photo on the right, you can see the base assembly form area removed, but the soil is not yet backfilled. And then finally, this is the completed photo with the soil backfilled, covering up the portion that contains the base plate assemblies. And you can see the UHPC going all the way up to the bottom of that, the crash strut. So a number of conclusions I have here. So first of all, PennDOT championed this project, which was the first and still the only, to my knowledge, use of UHPC for steel column repair in North America, at least in the transportation sector. Due to site constraints for material delivery, the use of UHPC for encasement and repair of the steel columns facilitated a rapid placement over a regional rail facility. UHPC provides long-lasting protection against future corrosion due to extremely low permeability. And due to its high flowability, the steel-like UHPC easily flowed through the contractor's 6-inch Trammy line and the 4-inch reducer, allowing all mixing and discharge to take place above and outside the tunnel. Mixing the steel-like UHPC in standard ready-mix trucks provided the contractor numerous advantages that helped accelerate the UHPC placement and reduce waste. And the unique properties of steel-like UHPC also provided the contractor lots of time flexibility when formwork problems arose, without ever having to waste any UHPC in hot weather conditions. So that is the end of our presentation, and if time allows, we'd be happy to take any questions.
Hey, Mike, while we're waiting, I have a good question from the other presentation. How does UHPC handle mass concrete? Does it have issues with heat, or any ideas? I've never heard of anybody using it yet. Obviously, expensive stuff, but yeah, be interesting to know if that had any susceptibility to the mass concrete required criteria.
Well, UHPC loves heat. Heat helps it cure faster. I'm sure there is a limit beyond which heat becomes a problem, but I don't think there's any practical limits. In fact, autoclaving is used to create precast UHPC with even higher strengths. So I don't think that's a practical concern. And as you noted, mass UHPC construction, you probably have a hard time financially justifying that. You'd be better using conventional concrete and then putting UHPC around it to seal it.
Yeah, eventually, if it ever could get the price lower down closer to conventional, then then, that might be, with all the cooling and other stuff that you would have to do on top of it, maybe there's a break even point, that they can get to, but that's cool. Thank you.
Perhaps.